I had a dream.
So the parts of a wave, you got the crest and the trough. And the wavelength is the distance between two crests or two troughs, like so. And then you got your amplitude. And then you got longitudinal waves. And it's like with Slinky when you like pushed it forward, and that's like sound. And they vibrate parallel, which is like what it's doing here. And then transverse is where you just flung the Slinky up and down, like so. Now in overtones and harmonics, you got the fundamental frequency, which is the first harmonic, and it's one loop. And the second harmonic is two loops, and the third harmonic is three loops, and it's a constant. That's how you find the fundamental frequency. And resonance is all this jazz. So this is like where it's gonna make a sound. It's a fun time. Natural frequency. So standing waves are two different waves traveling in the opposite direction. And a node is when your amplitude's at 0, and then an antinode is where your amplitude is at its maximum. And then the distance between two nodes is wavelength over 2. So this is standing waves in tubes, and it's like vibrato kind of on a wind instrument. The length will change based on like the tube, like if there's openings and both ends are just one, or if it's closed. And those are all the lengths and wavelengths and examples, like so. And finally, the Doppler effect, by definition, is an increase or decrease in frequency of sound as the source and observer move towards or away from each other. And here's the formula for the Doppler effect. And when you're moving away from something, you use a plus sign. And when you're moving away from something, or moving away, you use a plus, and moving towards, you use a minus. So these are all the units for the Doppler effect. And you plug those in, and then get you your stuff. And this is our example.
Okay, for question 1, the figure above on the left shows a uniformly thick rope hanging vertically from an oscillator that is turned off. When the oscillator is on and set at a certain frequency, the rope forms the standing wave shown above on the right. P and Q are 2 points on the rope. Part A asks for the tension at point P is greater than the tension at point Q. Briefly explain why. So, for part A, you have to draw a free body diagram. As you can see, force of tension is equal to the force of gravity. And over here you can see force of gravity is equal to mass times gravity. M being the mass of the rope, and gravity is equal to 9.8 m per second squared. And so since point P has more rope under it, it has more mass. Therefore, point P will have more tension than point Q, since the force of tension is equal to the mass times gravity. Okay, so for part B, a student hypothesizes that increasing the tension in a rope increases the speed at which waves travel along the rope. In a clear, coherent paragraph-length response that may also contain figures and/or equations, explain why the standing wave shown above supports the student's hypothesis. So the first thing that we need to do is have a topic sentence. So our topic sentence here is, increasing the tension in a rope increases the speed that the waves travel along the rope. Since velocity equals frequency times wavelength, this formula can be used to find the speed of a wave. And since wavelength increases towards the top of the rope, just like force of tension increases the higher a point is on the rope, they are directly related. Therefore, the longer a wavelength is, the higher its tension. We also know that when the wavelength increases, the velocity also increases due to the formula velocity equals frequency times wavelength. And this is also supported because the frequency is kept the same in all of the strings since it is established by the source. So since tension increases as the wavelength increases, it is apparent that the velocity also increases when tension increases. Okay, for question 2, the figure above shows a string with one end attached to an oscillator and the other end attached to a block. The string passes over a massless pulley that turns the negligible friction. 4 such strings, A, B, C, and D, are set up side by side, as shown in the diagram below. Each oscillator is adjusted to vibrate the string at its fundamental frequency F. The distance between each oscillator and pulley L is the same, and the mass m of each block is the same. However, the fundamental frequency of each string is different. The equation of the velocity v of a wave on a string is v equals square root force of tension divided by m divided by L, where force of tension is the tension of the string and m divided by L is the mass per unit length, in parentheses, linear mass density of the string. So part A asks, what is different about the 4 strings shown above that would result in their having different fundamental frequencies? Explain how you arrived to your answer. So, for part A, our topic sentence is that the m divided by L for each string is different. So since L is the same for all of the strings, the wavelengths must also be the same. And because of the formula V equals frequency times wavelength, we know that the velocities of the strings must also be changing since the frequencies are changing while the wavelengths are kept the same. Given that V equals square root force of tension divided by m divided by L, and that force of tension is the same for all of the strings, it must be m divided by L that is changing to result in the changing velocities. So for part B, a student graphs frequency as a function of the inverse of the linear mass density. Will the graph be linear? Explain how you arrived to your answer. So, for part B, no, the graph will not be linear. So in order to do this, you have the 2 velocity functions, which is velocity equals square root force of tension divided by m divided by L, and you also have velocity equals frequency times wavelength. So what we need to do is put these 2 formulas, we need to set them equal to each other. So in the end, we will get this. Once we have this set up, we need to put this into the y equals mx plus b format. So in order to do this, we are solving for frequency. So as you can see here, we divided the rest of this by wavelength. So we get frequency equals the square root of force of tension divided by wavelength times 1 divided by the square root m divided by L. So this fits so this fits the y equals mx plus b format. And since the function that we end up with is 1 over square root m divided by L, it is not equal to the function 1 divided by m divided by L. So therefore, this equation is not linear.